Hi, I'm Steven Zoe, a high schooler from Cheyenne Mountain High School. I'm working for the UCCS Vision and Security Technology Lab, and here's our paper CAST, Conditional Attribute Subsampling Toolkits for Fine-Grained Evaluation. So, in facial recognition, there's many possible evaluation categories, from low versus high quality sets, different demographic sets, atmospheric conditions, and facial attributes. You can have any combination of these sets, but you don't necessarily want to spend too much time organizing these sets and hand creating them for evaluation. And that's where our toolkit comes into play. CAST filters through large data sets based on criteria and attributes that you specify. From there, these subsets are then automatically evaluated for performance, and this all works with a single script. So here's our implementation details. So with this script down here, we gather column indices, we filter based on criteria and attributes that you specify, and then from there, these subsets that are created based on the criteria and attributes are saved as CSVs, while also being evaluated. We demonstrate CAST on WebFace42M, a dataset of 42 million images and 2 million identities. We calculate out attributes and use CAST to generate subsets for evaluation. So here are a few of our attributes that we collected. We used affect to collect facial hair, sunglasses, hair color, hat, presence, etc. We use fair face to collect race, gender, and age, and we have a couple image quality models on the right. Now these are pre-computed, and these values are available on our Git for download. So we subsample through WebFace, and the first implementation was on image quality assessments. So we filtered based off the image quality that these models gave us, and we found that brisk impact to pic correlated with performance, while NEMA did not. We found MagFace, SDD, FIQA were the best predictors. Now we also filtered across demographics. So on the left we have the distribution of demographics computed with the Fairface tool. And on the right, we have our results when running across these different demographic sets. So on average, we have about 99.18% accuracy, but there's a problem. There's not a lot of differentiation between these results. The lowest score is around 98%, the top score 99%. And we can't really tell where our facial recognition models are failing, which is a problem, because we want to be able to find and treat each demographic with equality. And that's why we created the CAST benchmark, the C11. So we went into WebFace42M and we collected all the images and identities that that facial recognition models had the hardest time categorizing and identifying. And then we created 11 sub-benchmark categories with these images. We then ran a few of the state-of-the-art facial recognition models on these 11 sub-benchmark categories, and here are our results. As you can see, there's a lot more differentiation between these demographics, and that provides a lot more insight on where models are failing. And this is important because, again, we don't want to have data sets that are littered with easy to classify and identify images, because it doesn't really give us a good idea of where our model needs to improve. Our future for CAST, we want to have CAST be able to create optimal training distributions. But for now, here is our code, and thank you for listening.